Yeah, hi guys. So I need to solve one or two questions with you as regard this Doppler effect that involves the wind, and I have this question which I have solved already. Let me quickly explain this question with you. And now you have an ambulance is moving at 30 meters per second towards a stationary person standing by the roadside. So here is the ambulance on the road, and we can have the observer which is on the other side of the road. Its sirens emit a frequency of 600 Hz. Now, here he made a siren which has a frequency of 600 Hz, and that is our frequency of the source. Now, our concern here is this one. There is a strong tailwind blowing at 20 meters per second in the same direction as the ambulance. As the ambulance is moving towards the observer, then we have the wind also blowing directly towards the observer. Now, what does this imply? Since both of them, the wind and the wind and the sound waves, they move in the same direction, then what does that imply? It means the waves will be compressed, thereby the crest to crest will be very minimal. In that wise, you will have a very short wavelength for that sound wave. However, this will increase the frequency of the wave. Likewise, it will increase the speed of the wave. So what does that imply? It means that in the Doppler effect equation that we know, so whatever will happen, we will add the wind speed, which is 20 meters per second, to both the numerator and the denominator of that equation. Meaning that from the equation we have F naught equals to Fs V over V plus or minus Vs. So what you just need to do, add 20 to up and down. You know what it does? That you know what it means? To cancel the effect of that wind. That is the reason why you add it, because the wind and the sound wave, they are moving in the same direction. Thereby the sound wave will have more increase in the velocity. So that is the reason. Then that wise you get this equation here, which is F naught equal to 600 plus into 3D blah blah blah. Then you get the answer, which is 654.4 Hz. Okay, we'll also be looking at this question also relating to this Doppler effect with wind, and the question says a delivery truck is driving away from a stationary traffic observer at a speed of 20 meters per second. So here we have the delivery. This is the delivery truck here, and moving with a speed of 20. This is the speed with speed of 20 meters per second. Then as it's moving away, we can see that the sound wave, here is the sound wave going away from the observer, and as the sound wave is moving away from the observer, what we can see is the wavelength start increasing, that the crest to crest is increasing. Okay, as the crest to crest is increasing, that shows that the wavelength will also increase. And you know what that means? Once the wavelength is increased, then we have a lower speed. That is, the speed of the sound going there will become slower. Okay, then not only that, find this is the frequency of the emitting sound from the engine, but we have the wind blowing towards the truck in this way. It is blowing against the direction of the sound wave. Therefore, what does this one imply? It will keep widening the crest to crest, thereby slow down or decrease, cause a kind of decrease in the speed of sound going to the observer. What does that imply? Since the wind is blowing against the sound wave, what we just need to do is we need to cancel the effect of this wind, and to do that, simply minus the speed of the wind from the speed of the sound wave. Thereby, we can now go back and apply this into the Doppler equation, as you can see from here in the Doppler equation. Now we can have this is the 450, which is the Fs, and here is the v, which is the speed of the wave, and now you can see I minus the speed of the wind, because the wind is going against the direction of the sound wave. Okay, so as I have done that to the numerator, I will also do that to the denominator. Do not forget, because the source of the sound wave is moving away from the observer, we use plus. However, to cancel the effect of this the wind, I minus the speed of the wind from both the numerator and the denominator. The reason why I minus in this case is because the wind is blowing against the direction of the sound wave, and that gives us a final answer to be 424.3 Hz. Yet we have another question to look into. In this case, you have a motorbike passes a stationary observer at 25 meters per second, which is the normal, the PS. The engine sound is 500 Hz, that is our Fs. Wind is blowing at 15 meters per second perpendicular. Please, I would align this word perpendicular to the road, that is from the side. What is the frequency heard by the observer as the motorbike approaches? Another thing here is this: the motorbike approaches. Already, don't forget, the motorbike passes a stationary observer, but before it passes, this is what you are looking for. Before it passes the observer, so please take note of this one. Now, in this case, we are not doing anything. We apply the Doppler effect equation as well, but in this respect, the wind is perpendicular to the sound wave. Do not forget, the sound wave is a longitudinal wave, and that means it travels only in one direction. That the propagation of the wave and the energy of the wave, they are in parallel to each other. Therefore, the wind blowing perpendicular to this sound wave will have no effect. I repeat, will have no effect on the speed of the sound wave. Therefore, you just apply the Doppler equation as normal equation that we have before, without including the wind speed, either minus or plus. Okay, and let me put this one in another case. Let's say, I don't know if you have idea of this one. Let's say you have because speed, or let's say velocity, is a vector quantity. Now the speed, the velocity of this sound wave, it is going in the horizontal direction. Now we have this is the speed of the sound wave. We have the speed of the wind, or the velocity of the wind, perpendicular. For you to resolve this to the horizontal, we have to use this equation. I don't know if you know, have idea of this equation, that V of horizontal equal to V cos theta. And in this case, what is the cos theta? Because of perpendicular, the cos theta is 90. If you take a cos 90, you will realize that it will give you 0. That is another reason why this does not have effect. The wind does not have effect on the speed of the sound. However, let's say it is not perpendicular, but it's at an angle. Let's say the angle of 30, 60, 45, and the likes. So what you need to do is to find the effect by when you resolve it horizontally. The value you are getting from here is what you now either minus or subtract from the speed of the sound wave. So let's not go into that, but now just realize that whenever you have the speed of the sound and the wind perpendicular to each other, so please immediately neglect the speed of the wind and solve the equation as the normal, as you can see, which I have solved in this case. Don't forget when it is approaching, so we'll use minus in the denominator, and that gives us a 539.8 hertz.